Of all the natural threats facing our planet, the most powerful ones emerge from within. Beneath Earth's crust lie more than 1,500 potentially active volcanoes. In an average year, between 50 and 70 volcanic eruptions occur, typically small and localized. But what would happen if all of these volcanoes erupted at once? The effects would be immediate. Across every continent, from the Andes to Iceland, from Kamchatka to the East African Rift, columns of ash, gas, and molten rock would surge skyward. Pressure stored in magma chambers would be released simultaneously, triggering thousands of explosive eruptions. The volume of volcanic material ejected would dwarf annual global output. A single major eruption like Mount St. Helens releases about 1 cubic kilometer of ash. In this scenario, the combined output would exceed 10,000 cubic kilometers. Atmospheric density would rise dramatically in the first hours. Volcanic ash composed of fine rock particles would enter the troposphere and rise into the stratosphere, partially blocking incoming solar radiation. Even before ash settles, daylight would begin to dim across much of the globe. Within 24 hours, average surface temperatures would drop by several degrees Celsius due to increased atmospheric albedo. Volcanic gases, particularly sulfur dioxide, would react chemically in the atmosphere to form sulfate aerosols, tiny reflective particles that further reduce solar penetration. The outcome would resemble the aftermath of the 1991 Mount Pinatubo eruption, but magnified by several orders of magnitude. That eruption alone lowered global temperatures by half a degree Celsius for 2 years. In this case, a temperature drop of 3 to 6 degrees is likely within months. A phenomenon known as volcanic winter would begin. Seismic activity would spike in tandem with eruptive forces. Tectonic plate boundaries, subduction zones, and rift valleys would experience increased fault movement. Earthquakes ranging from magnitude 7 to 9 would become frequent. Many would trigger massive tsunamis. Coastal regions worldwide would face waves traveling up to 500 miles per hour. Air quality would collapse on a global scale. Volcanic ash contains silica, aluminum, and iron oxides, hazardous when inhaled. Respiratory illnesses would become widespread within hundreds of miles of eruption centers. Even areas far from volcanic zones would experience reduced visibility and hazardous air quality. Air travel would cease entirely, as even minor ash concentrations can destroy jet engines. Ground transportation would also suffer. Ashfall accumulates into thick, abrasive layers that clog air filters and overheat engines. Roads become slick and nearly impassable. Visibility drops to just meters. Electrical grids would begin to fail, as ash and acid rain, formed when volcanic gases react with atmospheric moisture, corrode power lines and transformers. The chemical composition of precipitation changes drastically. Acid rain with a pH below 4 would destroy crops, acidify water bodies, and erode infrastructure. Agricultural systems would collapse within weeks as photosynthesis grinds to a halt. Natural food chains begin to destabilize.
As concentrations of aerosols and ash increase in the atmosphere, global air circulation begins to break down. Jet streams, which determine weather patterns, start to shift. In tropical latitudes, precipitation ceases, triggering widespread drought. In temperate and northern regions, by contrast, abnormally large amounts of precipitation fall, now in the form of snow and highly acidic rain. Soil erosion intensifies, and agricultural regions lose fertility. Grain crop production halts across all growing zones during the very first season after the eruptions begin. Agricultural collapse is compounded by biological breakdown. The mass disappearance of sunlight suppresses photosynthesis. The amount of oxygen produced by plants drops. In the marine environment, phytoplankton, the planet's primary oxygen producer, suffers. This sets off a chain reaction. Zooplankton, Fish and marine mammals begin to experience oxygen starvation. Ocean productivity declines. In coastal ecosystems, anaerobic decomposition of organic matter begins, releasing methane and hydrogen sulfide, gases toxic to all forms of life. On land, the situation worsens with the collapse of global transport and logistics infrastructure. Ports are paralyzed by low visibility and ash deposits. Railway lines become blocked, and road traffic comes to a near-complete stop. Water and food shortages spread. Urban water intakes and treatment facilities become clogged with volcanic ash. Even fresh water becomes unsafe to drink without multi-stage filtration. Volcanic winter begins to pressure both the biological and structural resilience of buildings. With a sharp drop in temperatures, infrastructure designed for normal climate loads fails. In the northern hemisphere, where most of the Earth's population lives, heating systems collapse. Without solar heating, and with temperatures dropping below -20 degrees Celsius in areas unprepared for such conditions, mass freezing of buildings begins. At the same time, accelerated glacier melting is triggered by tectonic activity. Volcanic eruptions beneath ice sheets in places like Iceland or Antarctica produce lava flows that rapidly melt ice. Vast amounts of fresh water are released into the oceans. This disrupts thermohaline circulation, the main mechanism for heat distribution in the global ocean. The Atlantic Gulf Stream weakens. Europe faces extreme cold, while other regions begin to flood from rising sea levels. The total carbon dioxide emission from all eruptions exceeds 500 gigatons. This is equivalent to several decades of anthropogenic emissions. Despite the reduction in sunlight, the concentration of greenhouse gases in the atmosphere continues to rise. The dual impact, cooling from aerosols and long-term warming from CO2, creates an unstable climate regime that will last for decades. Within a few weeks of the onset of eruptions, the entire planet is covered in a dense haze. At sea level, visibility drops to just a few hundred meters. Satellite navigation and telecommunications are disrupted. Electromagnetic radiation from volcanic plasma emissions causes radio interference. Some low-orbit satellites are damaged by microparticles and lose orientation. The medical consequences become global. Volcanic ash particles smaller than 10 microns penetrate deep into the lungs. The incidence of respiratory disease rises exponentially. Among vulnerable groups, children, the elderly, and those with chronic conditions, mortality increases. Widespread outbreaks of infection caused by deteriorating sanitation become a new phase of the humanitarian crisis.
Several months after the onset of the global volcanic eruption, the planet enters a phase of long-term climate transformation. The average annual temperature drops by 4 to 6 degrees Celsius, and in some regions, by as much as 10. These conditions are comparable to those of the last ice age. In temperate latitudes, summer frosts occur, and winter begins 1.5 to 2 months earlier than usual. Permafrost expands, occupying new territories. In the southern hemisphere, weather anomalies lead to prolonged monsoon seasons and widespread flooding. The drop in temperature shortens the growing season. Plants can no longer complete their full development cycle, and yields plummet. In tropical zones, drought and acid rain decimate crops. In temperate regions, cold and lack of sunlight do the same. A global food crisis becomes inevitable. Food reserves begin to deplete within 6 to 8 months. The supply and production systems are destroyed, and the agricultural sector cannot adapt to the new conditions. Ecosystems enter a phase of cascading extinction. Species with narrow ecological specialization are the first to vanish. Tropical insects, coral polyps, amphibians. They're followed by mammals, birds, and large predators whose food chains collapse. The biosphere loses its stability. A mass extinction, similar to the Permian-Triassic event, accelerates. Back then, up to 90% of marine species and over 70% of land species disappeared, possibly due to massive volcanic activity. The world's oceans also undergo catastrophic changes.
Large volumes of nutrients from soil erosion lead to eutrophication, excessive organic matter, and oxygen depletion. This creates dead zones, especially in coastal waters. Thermal imbalance disrupts migratory routes of marine species. Cetaceans lose orientation due to shifts in magnetic fields caused by volcanic activity and tectonic plate movements. Rivers and lakes become oversaturated with acid-forming compounds. Many bodies of water become uninhabitable. Plankton, fish, and amphibians die off. The freshwater crisis worsens. Filtration systems fail, and sources are contaminated not only chemically, but also biologically. In the absence of sanitation control, outbreaks of cholera, dysentery, and other waterborne diseases begin to spread. Infrastructure continues to deteriorate. The weight of ash exceeds structural load capacities. Roofs collapse, especially in humid areas where ash turns into a heavy paste. Lahars, mud flows formed from a mixture of water, ash, and volcanic debris, begin descending slopes. They travel at speeds of up to 60 kilometers per hour and can reach densities of 2 tons per cubic meter. Lahars destroy everything in their path. Vast areas previously suitable for habitation become uninhabitable. Evacuation is impossible. Transport and logistics networks are destroyed. Millions of people are cut off from the outside world. Mobile communication is gone, and the internet is inaccessible. Energy systems across much of the planet are paralyzed. Nuclear power plants, deprived of cooling, enter automatic shutdown mode, but in some cases, radiation leaks may occur if backup systems fail. The role of governments weakens amid the global crisis. Humanitarian aid becomes impossible. Resources are limited, coordination breaks down. Local conflicts erupt for access to clean water, food, and shelter. Global migration takes on a chaotic character, but most routes are blocked. The world's major cities are either abandoned or have become hotspots of epidemics and industrial disasters. The layers of ash that settle on the Earth's surface alter its albedo. Sunlight is reflected more, intensifying the cooling effect. In high latitudes, ash covers ice and snow, reducing their reflectivity and contributing to localized melting. However, the overall effect leads to sustained planetary cooling. The climate system enters a new equilibrium, significantly different from the previous interglacial regime.
1 year after the onset of the global volcanic eruption, the atmosphere remains saturated with aerosols. Solar radiation is reduced by 20%. The average global temperature has dropped by 8 degrees Celsius. Cooling reaches extreme levels. In temperate regions, summer temperatures do not exceed 10 degrees, while winter temperatures fall to -30. Most of the planet enters a period of perennial glaciation. A new snow ice cover forms, continuing to grow due to increased reflection of sunlight. Volcanoes are still active. Some, like Mount Ea in Indonesia, Mount Etna in Italy, and Kuchevskaya Sopka in Kamchatka, continue to erupt at intervals of several weeks. But a significant number of magma chambers have already emptied. In their place, calderas form, giant depressions left behind after eruptions. These structures can reach tens of kilometers in diameter and may trigger new localized catastrophes such as collapses, earthquakes, and hydrothermal activity. After 5 years, the planet's ecosystems reach a new equilibrium. Many species have gone extinct, but some have adapted to the new conditions. Organisms resistant to cold and nutrient-poor soils begin to spread. Certain bacteria and fungi that feed on volcanic minerals take over vast areas. Lichens, mosses, and frost-resistant shrubs begin colonizing regions left barren by the disappearance of previous vegetation. Industrial civilization has effectively ceased to exist. Without power, logistics, or global infrastructure, production has stopped. Cities, now abandoned and decaying, succumb to erosion,
freezing, and overgrowth. Within decades, most traces of human engineering will lie buried under layers of sediment, snow, and ash. Reinforced concrete and metal corrode. Only rare artifacts, made of stainless steel, ceramics, or glass, will survive as evidence of a once technological civilization. New biotopes form in place of former megacities. Remnants of urban flora, trees rooted in cracks in the asphalt, become the foundation for forest regrowth. Abandoned buildings are used by animals for shelter. Inside, temperatures remain stable, offering protection from wind and predators. Along ruined highways, the first forest strips appear. The biosphere slowly but steadily recovers. Atmospheric processes also enter a new phase. The gradual settling of ash and breakdown of aerosols lead to a partial normalization of climate conditions. 2 decades after the disaster, solar radiation levels returned to 90% of their original value. The average global temperature begins to rise slowly. The new glaciers start to retreat. River and lake systems reform, adapting to the altered landscape. The first migratory bird species return, but the biosphere is no longer the same. The loss of tens of thousands of species means that food webs have been rebuilt. Surviving species become dominant. Many of them are descendants of animals once considered synanthropic: rats, sparrows, cats, dogs. Evolution accelerates. In these selective conditions, only the most adaptive survive. This is a new chapter of life on Earth, in which humanity either no longer plays a role or persists as isolated, non-technological groups. The global eruption of all volcanoes became the most destructive event in the planet's recent geological history. Yet even this did not wipe out life entirely. Earth has entered a phase of recovery, once again proving the extraordinary resilience of its systems. The disappearance of technological civilization did not mark the end of the planet's story, only a shift toward a new evolutionary trajectory.